Now we're going to start talking about monitors, video game monitors, and the type of monitor that we use in games is commonly referred to as a raster scan monitor. Called a raster scan monitor. Your home TV is also a raster scan monitor. Regular television like this one is also a raster scan monitor, and I'll explain what we mean by raster scan as we go through this thing. I personally really like working on monitors. I think monitors are really a lot of fun to work on. They're pretty easy to work on. You see the same dozen or so problems over and over and over again, and of course I'll go over those. What we're going to do here in this lesson is first we're going to look at how monitors work. I'm going to go through everything about how the monitor works and all the different circuits in the monitor. We'll also talk about how they fail, which is more important than how it works. I don't really care if you know so much how, well, it's important to know how it works, but really it's important to know how the monitors fail. And then later on, after lunch, we'll cover the schematic diagrams. We'll go through all the different circuits on the schematic diagrams. I'll point out which parts fail and how to test them and all that kind of stuff. So for the first part of this, I just want to go through, I'm going to go through how monitors work in general. A video game monitor is basically just like a regular raster scan, regular TV at home, except that a video game monitor doesn't have a tuner. There's no way that you can hook up an antenna to this thing and get Bugs Bunny or anything like that. Now what that means though is that in a video game monitor we also do not have all the very complicated circuitry that we need to do that. In a regular television, the channel changer part of a television is fairly complicated. It's what we call RF, or radio frequency circuits. And RF circuits are really critical and really hard to work on. You really cannot use a meter to fix them for the most part. You have to have an oscilloscope. You even have to have a special probe on your oscilloscope called a demodulator probe. Also, in a regular television signal, in the broadcast signal, the black and white TV signal is transmitted in a different place than the color is. That was done in the beginning because they could not obsolete black and white TVs. When they first came out with color, they couldn't just obsolete all the black and white televisions overnight, and so they had to make them compatible. In the regular television, there's a circuit that splits the color and the black and white and recombines the two so that they're one on top of another, so you see a normal color picture. Well, we don't have any of that in a monitor. In a video game monitor, what's left in the monitor is all the easy stuff to repair. All the very easiest circuits in a television are what's left in a monitor, which is good because, we have to repair them a lot. We probably have one monitor failure every day at Area Amusements where I work. We have about 1,000 games, and we get about 5 or 6 monitors a week to repair. It's no big deal. It's real easy to sit down and whip out 4 or 5 monitors in a day, and you'll see what I'm talking about. Most monitor failures are really, really straightforward. So let's start taking a look at this thing. And the first thing we want to do is take a look at how the monitor is put together. Let's take a look at the picture tube. The monitor, we have this picture tube on here, and it's made out of glass, of course, and has this very thick glass front in it. Down in the neck of the picture tube, we have something that on the schematic diagram looks like this, and it's called the electron gun assembly. The electron gun assembly. And I have an electron gun here that I can show you. Pass this around so that you can take a look at it. This is the electron gun assembly from a carelessly handled picture tube. And in the end, you can see that there are actually 3 holes. There are the 3 holes. What are you looking for? No, it's mine. Get your freaking hands off my book. If you look, and I'm going to have to edit. See that? All right. Anyway, you can see the 3 holes where the electrons shoot out. Remember, the electrons are those little tiny negatively charged subatomic particles. Now, in order to get the electron gun to emit the electrons, it does have to be heated up. You know the orange glow that you see down here in the neck of the picture tube? That's what we call the CRT heaters. That's the CRT heaters doing their thing. Down here in the neck, as part of the electron gun assembly, on the schematic diagram, it just looks like little points like this. And they're actually connected together in series, like this. And these are the picture tube heaters, the heaters. They heat up the electron gun. That's real important. The electron guns are coated with a material that emits electrons. As a matter of fact, the part of the electron gun assembly that emits these electrons, and it emits like a ray or a beam of electrons, is a cathode. The actual part, the part of the electron gun assembly that emits the electrons is called a cathode. Remember when we were talking about the diode, we had the anode and the cathode. What a cathode really is something that emits electrons. What an anode is something that receives or collects electrons. And so that's what it really is. The part of the electron gun that emits the electrons is called a cathode. And in fact, the picture tube itself is referred to as the cathode ray tube. The picture tube is the cathode ray tube, or CRT for short. Cathode ray tube because the cathode is the thing that's emitting a ray of electrons, or a beam of electrons, and it is a vacuum tube. So these heaters are actually called the CRT heaters, the picture tube heaters. Anytime you hear the term CRT used in conjunction with a monitor, what they're talking about is the picture tube itself. The entire thing is the monitor. The picture tube with the electronic stuff that drives it is the monitor. The picture tube is the CRT. If you look at the electron gun assembly here, also there's this little gizmo right here. See this little thing that's hanging off the electron gun assembly? This little guy is called the getter, G-E-T-T-E-R. When they manufacture the picture tube, they have to get all the oxygen out of it. It's very important that they get all the oxygen out, because if they leave any oxygen inside the picture tube, the heaters will burn up. Just like there's no oxygen in light bulbs, there's no oxygen inside the picture tube. Inside the picture tube, it is a vacuum, meaning there ain't no air in there. Well, they originally suck the air out of the picture tube, out of the end of it, out of the end of the electron gun assembly. They can't get it all out. So they've got this little thing, it's called the getter, this thing that's hanging out here. And this is filled with flash powder, like the old-fashioned photographers used to use, flash powder. When they first fire up the picture tube at the picture tube plant, wherever that is, this thing flashes and burns up any oxygen that's left in the picture tube, any small amount of oxygen. It gets the oxygen out. Hence it's called the getter. Once it's used up, it just sits there. I'll pass this around so you can kind of take a look at it. Careful, the glass is kind of sharp, so don't touch it. Anyway, the electron gun assembly, as the name implies, shoots out streams of electrons. And there are actually 3 electron guns in the picture tube. Also, coating the inside of the glass front of the picture tube is a substance known as phosphor. P-H-O-S-P-H-O-R. Phosphor. Not phosphorus. Phosphorus is the stuff they make match heads out of. It's called phosphor. Now, there are actually 3 different kinds of phosphor coating the front of the screen. One type of phosphor is red, and one type is green, and one type is blue. And I can show these to you up close here. If you look at the monitor up here, here's the blue phosphor. There's blue phosphor glowing. There's the red phosphor. You can clearly see the difference there, blue and red. And then here's green phosphor. Red, green, sorry, yeah?
If there are bands of red and green and blue phosphor, how come the image is distributed all over the screen? How come the colors are distributed all over the screen?
Oh, well, I'm getting to that. Hang on a second. I'll tell you. That's a good question. These phosphor coatings are laid down in stripes across the entire screen. There's a stripe of red phosphor, and then right next to that, there's a stripe of green phosphor. Of course, they're very close to, much more close together than this. Green phosphor, and then right next to this, there's a stripe of blue phosphor. And each one of these guns is aligned so that its electrons will only strike one color phosphor. And so we have the red gun, and the gun itself isn't red, it just shoots out electrons that are aimed at the red color phosphor. The green gun, its electrons only strike the green color phosphor. And the blue gun, red, green, and blue. Now, they are not colored electrons, obviously. Electrons are just electrons. The color doesn't happen until the electrons strike the phosphor coating on the front of the screen. Red, green, and blue are the 3 primary colors of light. By combining red, green, and blue in different combinations, we can make any color that we want. For instance, if here's blue, just the blue phosphors are on. Here's red, just the red phosphors are on. Right next to it is magenta. Magenta is red and blue combined together. Look. Here's the blue color phosphor. There's the red phosphor. Watch what happens when I hit magenta. See, they're both on. Do you see how the red phosphor's on and the blue phosphor's on at the same time? You see the blank stripe in between, that's the green. It's off right now. There's the green phosphor only. If I combine green and blue together, I get a blue-green color known as cyan. And what you're seeing there is just the blue and the green phosphors only on. If I combine red and green, believe it or not, make yellow. You can clearly see there that the red phosphor's on and the green phosphor's on, and yet if I back up a little bit, well, it's kind of difficult to see here, but if you look at it directly, you can see this is yellow. And then white is all 3 on. See, all 3 of the phosphors are on. White is all 3. Now this is just a pattern generator that I have here, and you know, of course, in your game, it's the computer that sends this out. But there's just red. You can see the red covers the whole screen. There's just green. There's just blue. This is what we call a crosshatch pattern. Obviously, all 3 colors are on because it's white. In fact, I can show that to you. See, all 3 colors are on there. but just in those certain areas. And where there's no color at all, it's black, obviously. Where the phosphors are all turned off, it's black. Here's a dot pattern. And we use these patterns to do what we call converging the monitor, to line everything up. We'll talk a little bit more about that later. There's black. There's pure white. And then back to the color bars. So, by combining red, green, and blue in different combinations, we can make any color that we want. All three colors combined make white. The absence of all colors is black. And by combining them in different combinations, we can make millions of different colors. For instance, on my computer at home, I've got like a painting program. And it has a palette that you can adjust, how much red, green, and blue there is. And you can make any color you want, from flesh tones on up. I mean, that's what your regular TV is. This is exactly the same way that your regular television shows the picture that you see on the screen. So that's all there is to it. That make sense? That's pretty simple. Yeah. Anyway, red, green, and blue together make white, and the electron gun is now the electron gun assembly is now shooting out all three guns, and this is what you get. You get a spot right in the middle of the screen, just like that. Can you see the dot right there? I don't want to turn this up too high because it's possible to burn the phosphor coating. But all you have here is just this dot right here in the middle of the screen. Well, it would be awfully nice if we could somehow move that spot around. If we can move that dot around, we can make it draw some kind of a picture on the front of the screen. Unfortunately, the electron gun is fixed in the neck of the picture tube. The electron gun can't move around and scan around on the front of the screen. The gun just shoots straight ahead and makes this dot that we see right in the middle of the screen here. Well, that's not very good. Somehow we've got to move that beam around. And since we can't actually move the electron gun, somehow what we're going to have to do is deflect the beam. We're going to have to push the beam around. And the way we can do that is with magnetism. I've got some magnets here. Just some regular permanent magnets. Watch what happens when I hold the magnets near the screen. You see how I can kind of make that dot move. Now watch what happens if I hold the magnets down here near the neck. I can make it bounce all around. Not only that, watch this. I can make it split. You see the red, green, and blue? So magnetism can make it move around like that. But of course, unless you want to hire someone to hang out in the back of your video game and wave magnets around, somehow you kind of have to do it electronically. And there is a way that we can do it electronically. Mounted on the neck of the picture tube, there's something called the yoke. Down here on the neck of the picture tube, this guy right here, there's an electromagnet assembly, and it's called the yoke, Y-O-K-E. Now, all I've done here to get this spot on the front of the screen is I have simply disconnected the yoke. That's all I did to get that spot on the front of the screen. I simply unplugged the yoke. There's a connector down here that we'll see later on that I disconnected to. Well, when I disconnected the yoke, what we ended up with was just the dot on the front of the screen. Now, there are actually two different coils in the yoke. There are two different coils in the yoke, Y-O-K-E. One of them, all it does is make the beam move left and right. This is called the horizontal deflection coil. Horizontal deflection coil. The horizontal deflection coil is one of two coils in the yoke. The horizontal deflection coil. In the yoke, there are two different coils. It's actually two pairs of coils, but we can think of it as two different coils. One of them is called the horizontal deflection coil. It's called the horizontal deflection coil because the wide direction of the monitor is the horizontal direction. You know that a monitor is wider than it is tall, right? The wide direction is always the horizontal direction, no matter which way the monitor is turned. You know that we have some games where the monitor is turned like this. This is still horizontal. That's very important. This is a horizontal line. Right now you're looking at a horizontal line. I don't care which way that monitor is mounted. If you have a problem with a game and you call me up and say, hey, I got a problem, I've got a horizontal line, this is what I'm thinking. If you call this a vertical line, I'm going to send you in a whole different direction for troubleshooting because they're two completely different circuits. So the wide direction of the monitor is always the horizontal direction. And it's called the deflection coil because it deflects the beam. That is, it pushes it to the side, one side or the other. It's deflecting the beam. Golly gee whiz, what do you suppose we call this one? Sure, the vertical deflection coil, absolutely. Yeah, so we have the horizontal deflection coil that makes the beam move left and right. The other coil makes the beam move up and down. It is the vertical deflection coil. I'll just call it DC there. Vertical deflection coil. Together, these things make up the yoke. The horizontal deflection coil and the vertical deflection coil together as a unit make up the yoke. Now all I've done here, of course, is disconnect one or the other of the yoke coils. Let me go ahead and put these back in. Together, when the horizontal and vertical deflection coils are working together, what we end up with is a screen filled with white light like this. And when we have a screen filled with white light like this, this is known as raster. This is called raster. At the moment, we see a little bit of strangeness over here, and I'll explain what this is in just a second. But a whole screen filled with white light like this is called raster. It's important to be able to tell if you have raster, because if you can tell that you have raster, it means that certain things in the monitor have to be working okay. When someone calls me up for advice, and let's say they say, oh, I've got a problem with my monitor, the screen is blank, the first thing I'll ask them to do is turn up the brightness and see if they see raster. The brightness control monitor in the monitor is called the screen control, and I'll point it out to you in just a little bit. It's on the high voltage unit. It's called the screen control. See if you have raster. If you have raster, it must mean that certain things in the monitor are working perfectly okay. Obviously, to get raster, you have to make the beam move from left to right, the horizontal deflection coil in the yoke has to be working. And there's an electronic circuit that drives that. That's got to be working too. Same thing with the vertical deflection coil in the yoke. The vertical deflection coil in the yoke must be working, or all we'd have is a picture, a thin line across the screen. So the vertical deflection coil in the yoke's got to be doing something, and there's an electronic circuit that drives that as well. That's got to be working too. Obviously, there's a power supply in the monitor. That's got to be working. If the power supply was crapped out, I wouldn't see anything at all on the front of the screen. So just by reaching back here and cranking up the brightness control, the screen control, and seeing raster, it means that a bunch of stuff in the monitor is working okay. Now, at the moment, we've got a bit of color distortion here. And I can show that to you even more clearly with the color bars. You can see how messed up the color is. And if I put it on a single field, that's supposed to be pure red. This is supposed to be pure green. That's supposed to be pure blue. And you can see that it's all messed up. And the reason it's messed up is because I use some magnets on the screen. It doesn't take very much to move those beams around. And you saw how close together the phosphor stripes were. Well, watch what happens when you use a magnet on the screen. You can see the amazing magnetic field. In fact, you can even see fields attracting each other. You can see them repelling each other. When they repel, they look especially interesting.
Kaleidoscope.
Yeah, it's beautiful. Unfortunately, it magnetizes the screen like this. I got to one of my locations down by the Mexican border down there, and all my games look like this. They're all messed up. And magnetism is the thing that did it. Obviously, some kid found that magnetism does that, and he started waving magnets around and screwed up the screen. To prevent that from happening, there is something called a degaussing coil in the monitor. On the monitor, surrounding the picture tube of the monitor, zoom in for the folks at home here. There's this coil right here that surrounds the picture tube. It's right here too. Okay? It's called the degaussing coil. D-E-G-A-U-S-S-I-N-G, degaussing coil. The coil, not coin, degaussing coil. Gauss was an early experimenter with magnetism and electricity and stuff, and in fact our unit of magnetic strength is the Gauss. That's, well, one of our units of magnetic strength. Like, for instance, a typical little permanent magnet like this might be about 5 Gauss. A degaussing coil is a demagnetizing coil. The degaussing coil comes on automatically whenever you first turn the monitor on from a cold start. It only works when the monitor has been off for a while. It has to be off for about 20 or 30 minutes for it to operate. It automatically comes on whenever you first turn the monitor on and demagnetizes the picture tube. That's important because not just to keep kids from hitting the games with magnets, but the magnetic field of the Earth is what magnetizes the picture tube. The same thing that makes the compass needle point north also magnetizes the picture tube. In fact, sometimes you can see this. I don't know what will happen in this case, but if I move this monitor, you may see the colors shift as well. Yeah, definitely. Do you see down here in this corner? Watch this corner. See how it turns blue? Like that? And no, the magnet's way over here. It's nothing to do with that. It's just the magnetic field of the Earth. And sometimes you'll see this, especially in cocktail table games. You'll have a cocktail table game, it'll be set in this direction, it'll look perfect. You turn it 90 degrees, and the colors are all messed up. And the reason for that is that it's just the magnetic field of the Earth that's messing it up. Well, we have games in 7-Eleven stores. They're on 24 hours a day, 7 days a week. The degaussing coil never, ever, never operates, ever, in the 7-Eleven stores, because the games are always turned on. So you can get a degaussing coil. If you turn in your book, I think it's page 61. God, look at that, I turned right to it. On page 61, and you'll see a picture of this degaussing coil here. This small coil right here. Well, it's not that small. It's actually about this big. And they're about $40, and you can degauss the picture tube manually with that. But I've got a very cheap way to do it, and I borrowed this from Andy. You can also use a soldering gun as a degaussing coil. And here's how you do it. Hold the gun near the picture tube, energize the gun, and make it go in circles like this. This is a process called witch doctoring. and you repeat the following: Ham nakieto wiga spugish manga, and it clears it all up. Hango spenni mugish manga. Okay, so that when you get to a game, and if the colors are all messed up like this, instead of going out and buying a degaussing coil, just use your soldering gun. You start in the middle, you pull it out like this, ever-increasing circles, pull it away, turn it off, degauss. If it doesn't work the first time, like I see a little bit of blue down there in that corner, get rid of it like that. Yeah?
We're talking about big soldering iron.
Yes, we are talking about a soldering gun like this one, not a soldering iron. It has to be one of these pistols, because what it really is a transformer inside, basically, and it creates a huge magnetic field.
A drill or anything like that?
Well, supposedly a drill works. I've tried to drill a couple times. It didn't work with beans. Have you tried to drill? Did it work? It worked okay, huh? But the deal is, see, I can also kind of do it with permanent magnets. If I have it's gaussed, I guess you would say. If I take these things in my hand and kind of do that, see, I can get rid of it that way too. All you're looking for is a changing magnetic field. You just have to scramble up the particles that are magnetized on it. So if you have this problem, you could try degaussing the picture tube, and it usually works. One word of caution here regarding the picture tube and colors and things like that. Down here on the neck of the picture tube, there are some little tabs here, some little plastic tabs here, and they're actually attached to rings.
Yeah.
These rings here. Turn in your blue book here to next page, page 63, and you'll see a better picture of those rings. Those rings are called purity and convergence rings. When they first manufacture the picture tube, there's no way they can get all three of those guns perfectly lined up. It just doesn't happen. So those rings are slightly magnetic. By manipulating those rings, they do something called converging the picture tube. And what they do is use a crosshatch pattern like this and line up all three of the guns so that each gun hits the exact color phosphor. This is not an easy process to do. It really isn't, not at all. The point I'm making here is keep your dang fingers off those rings. Don't just mess with the rings. Don't go, hey, what do these do? And start messing around with them, because what you'll do is you'll separate the red, green, and blue. Maybe you've seen this before on your home TV or on a video game. You see like something's got a blue halo on one side, or red or green. That's when the images, the red, green, and blue, are not all superimposed properly, when the monitor is out of convergence, as they call it. So all I'm saying is don't mess with those rings. If you ever have to change the picture tube, the actual changing of the picture tube is quite easy. It's really easy to unbolt the picture tube and stick in a new one and hook it all up. That's no problem at all. Converging it can be a real pain in the ass. And I've had very little success doing it, actually. I really have. But sometimes it goes great. Sometimes I work 8 hours on the thing. I never get it converged at all. It's almost better for us, when you have a wasted picture tube, to buy a whole new cheap replacement monitor and save the chassis of your old monitor as a spare. Because a new picture tube's about $150, and a whole new monitor is like $250 or something like that, and you can easily spend a day trying to line it up and not even be successful at it. Some people really like to have a pattern generator. People that work on their benches all the time, they're working on monitors all the time, especially if they plan on doing any picture tube replacing. You have to have a pattern generator. Now, some video games have built-in test patterns. You've probably seen them. You turn them on and they have built-in test pattern. And a lot of people use those. They just have an old board that happens to have the test pattern. They just hook up the old computer board and just have that, sitting around in their shop. Well, let's see how the picture tube actually, how the monitor actually displays this raster that we see here. Remember, this whole screen filled with white light is called raster. The beams, or beam, let me just call it beam for the moment, the beams of electrons, let's just say that it's one beam, starts out in the upper left-hand corner of the picture tube. And the horizontal deflection coil in the yoke makes it move from left to right, and it draws a line as it goes. Now, it's really just a single spot, isn't it? It's really, and I showed that to you before when I showed you the dot right in the middle of the screen. It's really just a single spot. But as the horizontal deflection coil makes the beam move from left to right, we see it as a line. And the reason that we see it as a line is that the phosphor continues to glow for a split second even after the beam has moved away from it. You don't have to know this. It's called phosphor persistence, that it persists in glowing even after the beam has moved across it. You can see this at night. At night, when you turn your TV off, it glows, doesn't it, for a while? As a matter of fact, in a darkened room, if the TV is turned off and you take a penlight flashlight, you can kind of like write on the screen. You'll see that it glows. So even though, remember, it is just a single spot moving across the screen, we see it as a line as it goes because of this phosphor persistence. When the beam gets to the right-hand edge, it is turned off. The magnetic field quickly resets to bring the beam back to the left, where it turns on again and draws another line underneath the previous line. It only draws the line from left to right. When the beams are at the right-hand edge, they're turned off. The magnetic field resets to start the beam back at the left-hand side again, and it draws a line from left to right. When it gets to it actually takes, and you don't really have to know this, but it takes approximately 60 or so microseconds, 60 millionths of a second for the beam to move from the right side of the screen back to the left side. Yeah?
Does the beam only go horizontal?
I'm getting to that. I mean, at the moment, yeah, it's moving from left to right. But no, not really. I'll tell you in just a second. It's a good question. It takes about 60 millionths of a second for it to move from left to right. But it comes back very fast. It comes back in only 3 or 4 or 5 millionths of a second. So it really moves fast on the way back. This time when it's coming back from the right back to the left is known as the horizontal retrace. It's called the horizontal retrace because essentially it retraces its step. In other words, the beam moves more slowly from left to right, although 63 millionths of a second isn't what I would call slow, but it moves more slowly from left to right. But then it quickly moves back to the left again. Moves back from left to right, and then it quickly retraces its steps and moves back to the left-hand side again. So it's called the horizontal retrace. So again, the beam is turned on the left side. The horizontal deflection coil in the yoke and the circuit that drives it makes the beam move from left to right, drawing a line as it goes. Then, at the right-hand edge, it's turned off. We get the horizontal retrace that brings it back to the left, and it starts drawing again. Well, naturally, we don't want to draw any line on the way back. If we did, we'd see a line in between the lines like that. These lines, by the way, are called raster lines, and I'll explain that in just a second, why they're called that. But we don't want to have a line in between the lines on the way back. So the beams are all turned off on the way back, and there's a separate circuit that does this. There's a circuit in the monitor called the blanking circuit. And the blanking circuit turns off the electron guns during the retrace time. The blanking circuit turns off the electron guns during retrace. When the beam is at the right and it moves back to the left, we don't want to draw a line, so the blanking circuit activates. The way it works, starts on the left, turns on, moves from left to right. We get blanking, retrace. Draws the next line. Blanking, retrace. The monitor scans exactly the same way that you read. All right. Until finally the whole screen is filled with these lines, these raster lines, and that's called a field. Then the beam comes back to the upper left-hand corner, and before this thing has a chance to fade out, it does the same thing all over again. Comes back up to the top, draws each line again in the same place, comes back up to the top, and does this over and over and over again. It does this 60 times a second. The monitor paints 60 fields per second. That's the frequency of our vertical deflection circuit. Remember the vertical deflection coil in the yoke and the circuit that drives it. It's called the vertical deflection circuit. 60 times a second, it moves from the top of the screen to the bottom and then back up again. 60 fields per second. That's the same frequency as our AC power, isn't it? Our regular AC power is 60 cycles per second, or 60 hertz. It's the same frequency, but the monitor does not depend on our AC power to get that 60 cycles per second. If that was true, you couldn't have battery-operated TVs, could you? There is a circuit inside the monitor that generates that 60 cycles per second, and we'll look at it later on in this lesson. But 60 times a second, the beam moves from the top to the bottom and then back up again over and over and over again like that, filling the whole screen full of these lines. Now, your average video game picture is made up of approximately 250 lines. 250 individual lines, raster lines. Hopefully that doesn't surprise any of you that a picture is made of a bunch of horizontal lines. It's pretty clear when you look closely at a monitor that you can see that any TV picture is made out of these raster lines. Well, that's about half of the lines that's in your regular broadcast TV. In a regular television set, you see 525 lines. That's why regular television looks better than a video game. When you look at most video games, like even, let's say, Street Fighter, for example, and you see the guys on the screen, the graphics are excellent in that game, but they look a little bit blocky, kind of chunky, like they're made up of little tiny squares, which in fact they are. Where if you're watching TV and you're watching the Smurfs or Bugs Bunny or something at home, all the cartoons, they look real smooth, don't they? All the images are real clean. That's because there are more lines in your regular television. It has what we call better resolution. The more lines you have, the better the resolution is. Now, we do have some what we call medium resolution games. Paperboy, Championship Sprint, Super Sprint, APB, Hard Drivin', Race Drivin'. There's a couple of Taito games as well that had what we call medium resolution monitors in them. They're actually special monitors that show you about 400 lines or so. I'm not exactly sure. And in fact, they're a special kind of monitor with different components in them. They're not really interchangeable with normal TVs. Now, this monitor is fully capable of displaying a regular 525-line picture. Your regular video game monitor is perfectly capable of displaying a 525-line picture. But the computer isn't putting it out. And the reason the computer isn't putting it out is presumably because it would take more computing power to do that. That is, it would take more computer memory, which is expensive. The processor would have to be working faster. And they figure, well, look, it's just a video game. What's the big deal? We'll just do 250 lines or something like that, which is perfectly acceptable for most of our use. But like in a Laserdisc game, the monitor would be just displaying the 525-line picture, just that the computer doesn't put it out. Well, if the horizontal circuit is showing you 250 lines before the vertical deflection circuit makes the beam go from the top to the bottom just once, the horizontal circuit has to be working 250 times faster, doesn't it? 250 of these lines to just one pass one field. The frequency of the horizontal circuit is much higher. The frequency of the horizontal circuit is approximately 15,750 hertz, or 15,750 cycles per second. How many of you can hear that high-pitched squeal that a monitor makes when it's on? Let me see your hands if you can hear it. Okay. If you can hear that sound, what you're hearing is the horizontal frequency. You're hearing the 15,750 cycles per second. Whenever I turn on a monitor, I always listen for that squeal because it tells me that certain things are working. As soon as I hear that squeal, I know that the horizontal deflection circuit is working okay, because that's what's making that sound. And the power supply is okay as well. We'll talk a lot more about that squeal later on, because it also tells me that something else is working too, something very important. But that's the horizontal frequency. Well, because the horizontal frequency is working so much faster than the vertical frequency, when I said that the beam is at the lower right-hand corner, it moves to the upper left, I really lied to you. It really doesn't do that. Because the horizontal is working so much faster than the vertical, the horizontal circuit actually goes back and forth about a dozen times before the beam gets from the bottom to the top. And what really happens is this. By the time let me just draw it with a little better pen here. By the time that slowpoke vertical section gets the beam from the bottom of the screen back up to the top, it's actually zigzagged its way back a few times. Now, you don't see these lines. These lines, I'll demonstrate them to you in just a second, are called vertical retrace lines. There's a very important reason that I point these out to you. Normally, you don't see these vertical retrace lines because of the blanking circuit. The blanking circuit turns off the electron guns during the retrace time. Not only during the horizontal retrace, when the beam is moving from the right back to the left. Of course, we don't want to see a line in between the raster lines. But perhaps even more importantly, when the beam is at the bottom and it's got to work its way back up to the top, we don't want to see these vertical retrace lines, so the blanking circuit activates to turn off the electron guns during the retrace time. I can demonstrate these for you. Okay, now, if you look carefully at these lines, I want you to see this. You notice that these vertical retrace lines always look like they're going from lower left to upper right. Now, if you look at them carefully, you'll see that they look like they're going from lower left to upper right. And in this case, it's real difficult to see, but there is a little dim line that you can see on the way back. I guess I really can't bring them up any more than this. Some monitors you can really see them. Here you can see them now on that guy. Okay, vertical retrace lines. Okay, here's why I point them out to you. A lot of people, when they see these vertical retrace lines, think that it means that there's something wrong with the vertical deflection circuit in the monitor. Remember, the vertical deflection circuit is responsible for filling the screen from the top to the bottom. If you really have a vertical deflection problem, you will just see a line across the middle of the screen, or perhaps a picture that's only this tall. If you see the vertical retrace lines, perhaps you have a problem with your blanking circuit that's not turning off the guns during the retrace time. Or, as we'll see later on, you may have a problem with your color circuits as well. If the retrace lines are a certain color, red, green, or blue, like that, then you actually have a color problem. If the retrace lines are white, then you have a problem with the blanking circuit. I will tell you about this about 3 or 4 times before the end of the day, so don't worry, I'm just kind of introducing it to you right now. So really what happens is the beam zigzags its way up, makes it back to the upper left-hand corner, then the beam is turned back on and draws the normal raster, just like we see, until we have the whole screen filled with white light called raster. And it does this, 60 times a second, bzzz, 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 over and over and over again. Make sense? Okay, it's really quite simple. But how does it draw, let's say, an image on the screen? I mean, this, if I have this game right here, this is the white cow in the snowstorm game. This is not a real entertaining game. I'm not going to put any money in this game whatsoever. If somehow we can make some areas of the screen light and some areas dark, maybe we can draw some kind of a picture on the screen, and we can do that. Let's say, for example, that we just want to draw a box right in the middle of the screen for some reason. A cube or a square right in the middle of the screen. Let's see how it would do that. Now, the beam always starts out in the upper left-hand corner. No matter what the computer wants the monitor to draw, no matter what the monitor is showing, the beam always starts out in the upper left-hand corner of the picture tube. And we just want to draw a box in the middle. So as the horizontal deflection coil makes the beam move from left to right, the beam is kept turned off. So it isn't really a beam at all. The magnetic field thinks the beam's there, but it isn't really. It's turned off. It's off. Of course, it's always off on the way back during the retrace time. It's kept turned off. It's off, off. No shortcuts allowed. No matter what we want to show on the screen, it has to start out here and start scanning. It's off, it's off, it's off. Or it wants to start drawing the box, it turns the beam on and draws a line. Turns off, goes to the end, has to go all the way to the end. Retrace, off, off. When it gets underneath the first line, it draws the second line. Turns off, goes to the end. It's off, on, off, 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 on, and so on. Now, of course, the lines are a lot more closely spaced than this. Well, it's a square. Kind of like you, Jeff. It's a square. Ooh. Ooh, hiss. Don't hit me with that bag of heat sinks. Now we're done drawing the box. Now, of course, these are widely spaced, but, to Dan there in the back of the room, this looks kind of like a box anyway, or a square. You're the second person to give me a hard time about that. But whatever. A block. A tank barrier. Now we're done drawing the box, but even though there's nothing else on the screen, the monitor has to continue scanning. It has to continue going, no shortcuts allowed. Has to go all the way to the end, but it's kept turned off. The beam is kept turned off. Kept turned off, goes to the end, zzz, comes back up to the top, does this all over again. Where it gets to the point where it's at the box again, before that box has a chance to fade out, 1/60th of a second later, it draws the lines in the exact same spot, which is amazing considering how close and tight they are. Go in the exact same spot. In other words, before it has a chance to fade out, it brightens it back up again, goes to the end, comes back, brightens it up, and does this 60 times a second. Let's say it wants something to move on the screen. Let's say we want something to move on the screen, and as you can tell, I'm a really great artist, so I'll use Pac-Man as an example, because that's about the extent of my artistic ability here. So there's Pac-Man there. Now remember, it's really drawn one line at a time. Really, Pac-Man would be drawn, like that. Really. Kind of, sort of. All right, so it draws Pac here first. Then the beam goes to the end, comes back up. The next time, it draws Pac over here, and his mouth is closed a little more. Goes to the end, comes back. Next time, Pac's over here, and his mouth is closed completely. Goes to the end. Next field, open a little more. Goes to the end, comes back, open all the way. And what we see, of course, is waka. Right? Like that. It's animation. It's animation just like in a movie or something, where if you're watching a movie, it shows the guy here. Then the next frame, he's here. And he's here. And he's here. And you put it all together and the guy looks like he's trucking down the street. Fine. It's the same thing, except that with movies, it's 24 frames per second. and it shows you the whole slide all at once. In other words, the film moves up or down, whichever way it moves into the shutter. The shutter opens up, shows you a slide. Shutter closes, the film moves, next slide is there, and we see 24 frames per second. Same thing here, except that here we have 60 fields per second, and it must draw it one line at a time as it goes through like that. But it's animation, that's all it is. If the computer wants something to move faster, it moves it further each time. And it looks like it's going faster. If it wants something to move more slowly, it moves less each time, and it looks like it's moving more slowly across the screen. But that's all there is to it, and that's how it draws the picture on the screen. Now, naturally, it is the computer that's sending out the signal that tells the monitor when to turn on and off. We have the printed circuit board, PCB, logic board, whatever you want to call it, the computer board, and the monitor. And of course, in the monitor, there's the picture tube and the electron guns and all that kind of stuff. Coming out of the computer are three different signals, the color signals. And if you've ever done a conversion kit, you've seen these things. There's a red wire, and there's a green wire, and a blue wire. And these are outputs that come out of the logic board that go into the monitor. Referring to your extremely handy JAMA connector, which you don't really have to pull it out if you don't want to. The red comes out pin 12, the green comes out pin N, and the blue comes out pin 13. And usually they use color-coded wires, red, green, and blue wires, to make your job a lot easier. These color signals tell the monitor when to turn on and off. For instance, let's say the computer wants something to show red on the screen. It might put, let's say, 4 volts out the red wire, and that would turn on the red gun on the monitor and show you red on the screen. If it wants something to be red but not quite as bright, maybe it'll put out only 3 volts. That'll still turn on the red gun, but it won't be quite as bright. If it wants something to be really dim red, maybe 1 volt. And of course, if there's no voltage on the red wire, then there's no red on the screen. Same thing with green, same thing with blue. If it wants something to be magenta, remember, magenta is a combination of red and blue. It would put 4 volts out the red wire and 4 volts out the blue wire simultaneously, and it would turn on both guns, and we'd see magenta. Now, it's really, of course, just the red phosphor and the blue phosphor right next to each other glowing, but your brain puts them together, and it looks like magenta. If it wants something to be magenta but not as bright, maybe 2 volts out each wire. If it wants something to be magenta but more red than blue, maybe 3 volts out the red and 2 volts out the blue. Just all these are changing voltages. The higher the voltage, the brighter that color is. It's that simple. We do have a name for these signals. These 3 signals, these color signals that come out of the logic board that tell the monitor what color to show, are called the video signals. That's what video really is. Video ain't Bon Jovi and Metallica and Madonna and stuff. What video really is the signal that controls the electron guns. That's what video really is. Now, in addition to the 3 outputs, we have one more video wire that connects between the monitor and the logic board. Do you remember from the very first day of class we discussed a complete circuit? And I said that in order to have a complete circuit, you need to have a source, the source path, and then you also needed to have the return path. Remember that in order to have a complete circuit. Well, in this case, the source is the logic board, and the color signals are the signals that are going to the load, which in this case is the monitor. But remember, we have to have a return path. In addition to the red, green, and blue signals, there's another wire connected between the two, and that's the video ground. And that's our return path, the video ground. And so there are 4 wires that connect between the logic board and the monitor, red, green, blue, and the video ground. And on my pattern generator, they're here. Here's the 3 wires, the red, green, blue, although he didn't use the right colors in this case, which kind of sucks. But pins 1, 2, and 3 are RGB, pin 4 is the video ground. And they plug into the video connector, which is right there. And it plugs in just like this. Now you'll notice that there are 2 pins not used. See those 2 pins that are not used there right next to it? And I'll discuss those a little later on. And you probably won't ever actually ever use those pins. I'll tell you what they're for in just a little bit.
Oh, TV's going crazy. I mean,
Huh? Oh. Oh, that's okay. It's smarter than I am. Does this make sense so far? Okay, so these are just the 3 video signals. The more color you have, the more voltage you have, the brighter each of those colors is. And that's all there is to it. By combining them in different combinations, we can make any color that we want on the front of the screen. Turn in your blue book to page 67. And here on page 67, if you look at the illustration of the monitor right here, you see the 2 connectors that are for the inputs to the monitor. You see a 6-pin connector, and you see a 3-pin connector. You notice on the 6-pin connector, 1, 2, and 3 RGB. This is pretty standard. 1, 2, 3 RGB. 1, 2, 3 RGB. 1, 2, 3 RGB. And they're almost always the same. They're not all exactly the same, but it's pretty standard. Pin 4 is the video ground. And there's pins 5 and 6. It says do not use, and I'll explain what that's all about in just a little bit. Okay, pretty cool? Everybody cool on that? All right. So that's the video. Now, in order for the monitor to display a stable picture like this, somehow the computer and the monitor do have to be synchronized with each other. In order for the monitor to show a normal picture, somehow the computer and the monitor do have to be synchronized. In other words, remember that it's the logic board that is telling the monitor when to turn the beams on and off. For instance, the score displays, we want at the top of the screen, let's say. Well, if the monitor happened to be scanning in the middle of the screen at the time that the computer put out the score display information, the scores would appear in the middle of the screen. And that wouldn't be any good, and the picture would be split in half. The top of the screen would be in the middle, and the bottom of the screen would be on the top. Just as if you had to adjust the vertical hold, let's say, on your TV, and it was halfway up and down. So in addition to the red, green, and blue signals that come out of the logic board, there is another signal that comes out of the logic board that goes into the monitor, and it's called the sync signal. Sync, short for synchronization. Synchronization, abbreviated SYNC. Although you'll see some people abbreviate it SYNCH, but to me that looks like cinch, so I think it should be sync, SYNC. The best way for me to explain what sync is to simply show you what sync does, or discuss what happens when you don't have sync. And what happens is very simple. Oh, let me back up here for a second. There are two different kinds of sync signals that come out of the computer board. One is called horizontal sync, and the other one's called vertical sync. Horizontal sync, vertical sync. And by the way, you'll probably never have a sync failure. It's very rare to have a sync failure. Maybe you don't have it hooked up right, but the actual failure is very unlikely. If you have a problem with vertical sync, the picture rolls vertically like this. Pretty obvious that it's rolling, isn't it? The vertical sync signal keeps it from rolling vertically. Well, if you saw this on any TV, wouldn't you go right for the vertical hold control? Yeah. Of course you would. If you try adjusting the vertical hold control, and you can get it to slow down, but you can never get it to actually stop, and in this case, the vertical sync is working, so it will stop. But if you can get it to slow down, but it always drifts up and down and never actually locks in place, you can see this one trying to lock. If you adjust the vertical hold, you can't get it to lock in place, you have a problem with vertical sync. Not likely, by the way. I mean, these are very unlikely, but it's a part of the monitor I do want to explain to you. So when you think sync, well, is the picture rolling vertically? I mean, if I brought any kid in from outside and said, here, kid, fix this, he'd go for the vertical hold control and adjust it, and away you go. If you try adjusting it and it always drifts up and down, that's a vertical sync problem. Horizontal sync is just the opposite. When you have a problem with horizontal sync, the picture will shift left and right. And it's actually difficult for me to really show this to you right now, but loss of horizontal sync can look like this, and depending on the pattern I have on the screen, there's the color bars. If you try to adjust the horizontal hold, if you can't get it to lock in place, you have a horizontal sync problem. Now, actually, what I'm going to do right here is I'm going to disconnect the sync wire, and we're going to see both problems at once, because this will be a lot easier for me to demonstrate. Okay, first of all, let me try to keep it from rolling vertically, because that's the easiest to do. You see the black bar? Yeah. I'm trying to adjust it to stop, but I can get it to slow down and never stop. See how it's slowly drifting. Now, I'm going to try to adjust the horizontal hold here, and this is what it really looks like when you lose horizontal sync. You see how it's shifting left and right? There it's more obvious. I just can't get it to synchronize. I'm trying, I'm adjusting the horizontal hold. And look, see? Boy, that's really close, but you see how it's shifted left and right like that? Okay, this is what happens when you have a loss of sync. The monitor just doesn't know where to put things at all. And so it's doing that. And if I adjust the vertical hold, man, I can get it to really slow down, but you see how it never locks in place? And actually, what this monitor is really synchronizing on now is the black bar that's over here. If I remove that black bar, see what it does? Okay, so this is obviously an unstable picture. This is what happens when you lose sync. I simply disconnected the sync wire. I'm going to plug it back in, and you'll see it'll just snap right in place, hopefully, if I don't kill myself trying to plug in something with the power on, which is something you should never do. There we go. All right. So when you think sync, think to yourself, is the thing rolling vertically? I have a vertical sync problem. Is it shifting left and right? I have a horizontal sync problem. Okay? Make sense?
So to fix something like that, you would first go to the vertical or horizontal holds?
Yes.
And then after that,
yes. To determine what your problem is, sure, obviously try adjusting it first.
Yeah.
If you try adjusting it and you can never get it locked in place, that's your diagnosis. That is what has told you that, yes, I definitely have a problem with the vertical sync or horizontal sync or what. You'll probably never see this. In fact, on occasion, I've tried to simulate it in a lab, and I haven't been able to even make it fail sometimes. What's the problem, Jeff? Yeah, don't forget, if your monitor's turned sideways, of course, the vertical roll will look like this, won't it? So don't forget about that. Monitor doesn't care what kind of a game it's in, sideways or vertical or horizontal. It doesn't care at all. Now, in all of today's games, the horizontal sync, horizontal sync and the vertical sync are combined together and sent along just one wire. It's called composite sync. Composite sync. Even though they're sent along just one wire to the monitor can tell the difference between the two. And the way it can tell the difference between the two is that they are two completely different frequencies. The vertical frequency is very low, 60 cycles per second. The horizontal frequency is very high, 15,000 cycles per second, 15,750 really. So just like you can tell the difference between like a little girl's high-pitched voice and a grown man's manly macho voice, right? By the frequency, the pitch, the monitor can also tell the difference between the two. There's a circuit in the monitor called a sync separator that you don't have to know this because it never fails, that separates that sync back into its vertical and horizontal sync components and sends it to the deflection circuits to keep them in time. Essentially what the sync is like a drill sergeant calling a cadence to the monitor. It's saying, you know, up, 2, 3, 4, up, 2, 3, 4. It's keeping it exactly in line with what the computer's putting out. Make sense? Yes, Shirley.
Your older games, they used to have 2 leads.
Yeah, getting to that right now. Really good question. Good question. There are 2 different types of sync systems. I'm not talking about vertical and horizontal here. Here's what I mean. Our older games used something called positive sync. Our new games, all the latest stuff and the stuff for the past 8 years, I guess, to me that's still new, use negative sync. Here's the difference between the two. In a positive sync system, if I were to check the voltage on that sync wire, normally it would be 0 volts. To synchronize the monitor, it momentarily jumps it up to 5 volts and back down to 0 volts and makes a pulse that goes up like that. When the monitor receives that pulse, what it really does is initiates the retrace. The pulse, the sync pulse really tells the monitor, hey, stop drawing, start your retrace. Negative sync is just the opposite. Negative sync, the voltage on the sync wire is normally 5 volts. When the computer wants to synchronize the monitor, it drops it down to 0 volts and then back up. It's not a negative voltage really, but the pulse goes down instead of up, and so they call it negative sync. These are 2 different ways to accomplish the exact same thing. The American games all started out with positive sync, Japanese with negative sync, and since the Japanese have dominated our market, obviously, everybody's switched over to negative sync. The monitor can use either type of sync. These monitors have the capability of using either type of sync. And there's a separate connector for negative sync. If you look at your book again on page 67 and look at the connectors underneath the monitor here. 1, 2, 3 RGB. Pin 4 is the video ground. Pins 5 and 6 we do not use anymore. That is for positive sync only. The older games used these. And in fact, in the older games, the positive sync was separate syncs. Separate vertical and separate horizontal sync. They did not use composite sync. But the negative syncs are composite. And there's a separate little 3-pin connector that we use for negative sync. The separate little 3-pin connector, pin 1 is ground. It's the same video ground as pin 4 on the 6-pin connector, and you can put your video ground on either pin. It makes absolutely no difference whatsoever. They're connected internally inside the monitor anyway. You can use either one. I always use pin 4. And the reason I do that is after all the video connector, and it's called video ground, and so I put it there. But you don't have to. As you saw on the connector of this pattern generator, it is on pin 4. And then the vertical and horizontal negative syncs go into pins 2 and 3 respectively. Well, you'll notice that it shows here the sync going into pin 3. And it says the vertical input may be omitted. This is very important, and it's really important that I get your attention, that you understand what I'm about to go through here. Some monitors are designed for composite sync. They like composite sync. For instance, the Wells-Gardner monitors, as this one is, is a composite sync monitor. It likes composite sync. All the monitors made by Hanterex like composite sync. On these monitors, you want to run the sync, the composite sync wire, which comes from pin P of your JAMA connector. You want to run that composite sync into pin 3 only. Only run it into pin 3 of the 3-pin connector. Pin 1, 2, 3. Pin 1 is the video ground. You may choose to put that on pin 4. Pin 2 is for the negative vertical, and pin 3 is for the negative horizontal. You should take the composite sync that comes out of your logic board, out of pin P, and run it only into pin 3. What some people do is put a jumper to run the composite sync into both pins 2 and 3. On the Electro-Home monitors, and we'll look at these things in great detail later on, you do have to put that jumper in. The Electro-Home is designed for individual sync inputs. But if you run the composite sync into both vertical and horizontal inputs in a Wells-Gardner or a Hanterex monitor, you run into trouble. And what will happen is the picture will be unstable. It'll either be jittering like this, or in the Hanterex monitors, it'll roll vertically, as if you have no vertical sync. This can be very, very confusing. With that jumper in, the Hanterex monitor won't even sync vertically, and you'll think you have got some kind of a problem. You don't. Just don't put that jumper in there, and it'll be solid as a rock. Let me give you just a brief story about this, because to illustrate the problem, and because it's a common problem. I see it all the time. It's very simple once you understand it, so you need to pay attention to this. And I'll be done in just a couple minutes. All right. We had a Chase HQ driving game, Taito driving game. At the time, it made a lot of money in a 7-Eleven store. This was like our very best 7-Eleven, right by a high school. It was a 7-Eleven where, when they call in for service, basically no matter where you are, you drop what you're doing and you drive out there and you help them out. Well, there's 3 of us that do field service at area amusements, and the communication between us is not all that good necessarily. So we get a service call on this Chase HQ, and the complaint is the picture is rolling vertically. Serviceman A goes out there. Yeah, it's rolling vertically, no problem. He takes the back off the game, adjusts the vertical hold control, solid as a rock, buttons it back up, leaves. Next week we get another service call, same complaint. But now Serviceman B is on duty, and he doesn't know Serviceman A has been out there to do the same thing. He goes out there, it's rolling, he takes the back off, he adjusts the vertical hold, everything's fine, he buttons it up, he leaves. Well, I'm Serviceman C, and I've got a slightly different call. My service call isn't picture is rolling. My service call is, if you don't fix this piece of crap, it's going to be out on the street. I'm sure you've all gotten those kind of calls before. So I go out there, it's rolling, I take the back off, I adjust the vertical hold, it locks in place. But what I notice is I don't have very much range. You know how you adjust the vertical hold? Usually you can go way to one side before it starts to break. You go way to the other side, it goes the other direction, and you put it somewhere in the middle. Well, what I notice is I've got no range. I can just barely move that before it starts to break. I look over here, the jumper's in place. The jumper's in place. I take the thing out, I snip the jumper, point like this, solid as a rock. And now I have the complete range that I'm looking for. I can adjust it quite a bit either direction. So the point I'm making is this. When you have a problem with vertical sync, make sure that the jumper is not in there. When you do a conversion kit, here's what you do. Connect the sync to pin 3 only first. Turn the game on. If it is not rolling, leave it that way. If it's rolling, then you'll have to put the jumper in. But if it doesn't roll, do not put that jumper in. We still have to look at one more thing before we can truly understand how the monitor works. Let's go back to the picture tube itself. And remember, the picture tube's made out of glass. It's got this nice thick glass front on it. The 3 electron guns down here that shoot out these beams of electrons. The electrons strike the front of the screen and they make the phosphor glow. Well, we cannot allow those electrons to stay inside the picture tube. And they don't shoot out the front of the picture tube. The electrons, after they strike the front of the screen, don't come out of the picture tube because glass is an insulator and electrons don't go through glass. And besides which, if they did, you'd sterilize all your customers and you wouldn't want to do that. Maybe you would, I don't know, but that ain't what happens anyway.
Some of them are to start with.
After the electrons strike the front of the screen, they bounce off. They bounce off inside the picture tube. But we can't allow those guys to stay in there because remember that similar charges repel each other. Just like with magnets, if I try to put 2 of the same pole of a magnet together, they repel each other. Same thing's going to happen here. If I allow these electrons to stay inside here, they're going to form a negatively charged cloud down here in the bell of the picture tube. How is that going to affect the electron beam coming out of the electron gun? It's going to deflect it, push it away. It ain't going to hit the front of the screen. And unless those electrons can whack against the front of the screen at almost the speed of light, you're not going to see any picture at all. Because that's how it works. The electron gun puts what we call kinetic energy, the energy of motion, into those electrons. And that kinetic energy is transferred into light energy. That's that conservation of energy thing that we were talking about before, by the electrons. So somehow we have to get rid of those electrons. And this is what the high voltage is for. I think that most of you are aware that there is some high voltage that's used somewhere in a monitor, and here's what it's for. On the side or the top of the picture tube, there's a small metal plug that's molded into the glass of the picture tube. It's called the second anode. A-N-O-D-E, the second anode. And I'll show it to you shortly. The first anode is actually part of the electron gun assembly. The first anode isn't called first anode, though. The first anode is called the screen, also known as grid number 2, G2. Remember, I mentioned that the brightness control on a monitor is called the screen control. When you're adjusting the brightness control on a monitor, the main screen control, you're actually adjusting the voltage on that screen, which can be anywhere from a couple of hundred volts up to 1,000 volts or so. So that's really the first anode. We don't care about that. Let's just go back to the second anode. And the second anode is here. And I'll show it to you up close in just a second. Whoa, hey. The second anode is this thing right here. It's this thing underneath this connector right here. I'll take it off shortly and I'll show it to you. In fact, maybe I can show it to you on this one here. Hang on. Do we have a blank picture tube in the other room? Yeah. Oh, never mind. I got it right here. The second anode looks a lot like the freeze plug in an engine block, if you know what that looks like. There's the second anode right there. Now, it's not a hole. It's sealed up. It's not a hole that goes into the metal because, into the picture tube, because remember, there's a vacuum inside the picture tube, and if there was a hole in there, you'd let all the air into the picture tube. Or as one student tried to convince me, you'd let the vacuum out. Right, so we don't want to let that vacuum out. We've got to keep that vacuum in there. So anyway, also, it was serious too. It's like, no, I let that. All right. Also, coating the whole inside of the glass bell of the picture tube is a metallic paint called Aquadag. I have no idea why it's called Aquadag. It's not wet, so I really just have no idea at all why it's called Aquadag, but it is called Aquadag. Anyway, the aquadag coats the whole inside of the picture tube, meaning that when I connect something to the second anode of the picture tube, I am actually electrically connecting to this whole aquadag on the whole inside of the picture tube. And this guy is connected to the high voltage unit in the monitor. Let's find my high voltage unit here. The second anode is connected to the high voltage unit in the monitor, and there's the high voltage unit right there. This is a bad high voltage unit. I'll show you this up close later on. You can see it's like wiped out. It's always connected through this very heavily insulated red wire and goes into the high voltage unit. The high voltage unit creates about 20,000 volts. It's about 1,000 volt per diagonal inch of the picture tube. So on a 13-inch TV, it might be maybe 13 to 15,000 volts. On a 19-inch TV, about 19 or 20,000 volts. On a 25-inch TV, about 25,000, and so on. And it is direct current, and it is positive. Plus 20,000 volts DC, which means that the whole inside of the picture tube is charged at about plus 20,000 volts DC. Well, here's what happens. The electrons shoot out of the electron gun. Now remember what an electron is. It's this little tiny negatively charged BB kind of a thing. It strikes the front of the screen, strikes the phosphor, makes the phosphor glow, and then it bounces off. Well, after it's bounced off, it has lost all of its energy, but it still has a negative charge. That will never change. It's an electron, and electrons have a negative charge. Well, if I'm a little old negatively charged electron, I'm going to find plus 20,000 volts rather attractive, don't you think? Right? Opposite poles attract, just like opposite poles of a magnet attract. Same thing. Well, here's what happens. After the electron bounces off, it attaches itself to the nearest outside wall, charged at plus 20,000 volts, where it gets sucked along the wall and out the high voltage wire and into the high voltage unit. Presumably, eventually, it gets pumped back up somehow and shot back out at a later date. I'm not really sure how that happens, and I don't really care. But that's what the high voltage is for. The high voltage is there in a monitor to remove those spent electrons after they've struck the front of the screen. If for some reason you have lost high voltage, you will not see anything on the front of the screen. If you lose high voltage for some reason, you're not going to get any picture whatsoever, because it's going to leave those electrons in the picture tube and they're going to repel the beam as it tries to hit the front of the screen, and unless it can whack it at the speed of light, just about, you don't get any picture. But what this also means is that if you see anything at all on the front of the screen, if you see any kind of brightness at all on the front of the screen, and maybe it isn't correct, maybe it's just a line on the screen, or maybe it's rolling or some other problem, but if you see any kind of brightness on the front of the screen, you must have high voltage, huh? Because if you didn't have any high voltage, you wouldn't get anything at all on the front of the screen. So if you see anything, maybe it's rolling, maybe you're missing a color, maybe you got some retrace lines, whatever it is, your high voltage definitely has to be there. Now, many of you are aware that there's some high voltage that's stored somewhere in a monitor even after you turn it off. And, you know, that's probably why you're here in this class right now. All right. And you're right, there is. And it's the picture tube itself that stores the charge. The picture tube acts like a capacitor and stores the charge in the monitor. All right, well, right now the monitor is on, obviously. Let me turn the monitor off. Just this up. Okay, right now the picture tube is charged. There's like 20,000 volts, well in this case probably 15,000 volts in the picture tube. Why am I doing this? Because I'm an idiot. No, here's the deal. Even though the picture tube is probably fully charged right now, it is impossible for that charge to get out of the picture tube and to anything else on the monitor. Because in the high voltage unit, there are some diodes in there. In the high voltage unit, there are some diodes, and the diodes are facing this direction. Well, a diode's a one-way gate. There's no way for that electric current to get out of the picture tube to anything else on the monitor. Now, I can show you that the picture tube is charged. I can show you that the picture tube is fully charged here. If you take a clip lead and a screwdriver with an insulated handle, like and this one is insulated, ground the other end of the clip lead, connect it to the chassis, and if we listen, we might be able to hear the snap. Definitely. And yet, when I was touching the thing, I wasn't getting a shock at all. Let me turn it back on. You can hear it come on, you hear the static. Turn it back off. Now, naturally, you don't touch anything with the power on. But I can touch anything with the power off, except underneath that second anode cap, of course. You know, it's definitely charged. And of course, you never want to do this with the power on because you'll draw a big old 3-inch arc off the thing and you'll melt the end of the screwdriver. This happened to me in one of my lab sessions. I was over here with one group working on a monitor with this group over here, and from this corner of the room I hear this. You know, this guy had melted the end of the screwdriver. Everybody called him Screwdriver for the rest of the class. It was pretty funny. But the point I'm making is that I know people that are perfectly competent technicians that work on logic boards that are just scared shitless to work on a monitor because they don't know what they can touch and they can't touch. And the point is that not only can I touch anything with the power on, but I can work on the board, I can test transistors, I can solder, I can replace transistors. I do not have to worry about getting a shock. It's impossible for that charge to get out of the picture tube and out of the high voltage unit because of these diodes that are here. Now, I know people that are really paranoid about this, so paranoid that before they'll even pull a game out of a cabinet, they'll, try discharging it first. Well, as far as I'm concerned, in a way, you're putting yourself more at risk by messing around with the second anode than by leaving it alone. I mean, suppose you don't realize where this other end of this clip is, and it happens to be attached to your Wavos down here, and you go sticking that thing in there. Woo! That's really exciting. Okay.
Disco Duck.
Disco Duck, yeah, you talk like Michael Jackson for the rest of your life. But the point I'm kidding, obviously. But the point I'm making is that you do not have to be paranoid about the monitor. You don't have to discharge it after every time you turn it on and you go to work on it. Now, I've got one word of caution for you here. Let me turn it back on.
Did your isolation transformer hook up?
No, it's working. Didn't it?
Fuel ground? Green one?
No, it's working. Oh, that's all off anyway. If you discharge this once, let's say you're going to remove the chassis and pull the chassis away for repair. You discharge the second anode. Okay, definitely discharge. Using the grounded screwdriver, pull the second anode connector off like that. 2 words of caution. Number 1, when you go to put the second anode back in, you see the 2 little fingers there? Okay, you got to make sure that you get both of those guys in. Never depend on the suction cup action of this thing to hold it in place. I mean, it'll kind of act like a suction cup, like, if you put it on there, it'll hold on there, but it'll do that, and then it'll fall off. So you have to make sure that you get both of those little fingers on there. Use the grounded screwdriver, so when you put it back in, to put one finger in, and then make sure you use the grounded screwdriver to push the other finger back in there, and I'll do this in just a second. The other thing is, though, that when you pull the monitor chassis off, if you pull the chassis off and let's say you've set it on the bench to work on it, or you're swapping chassis out in the field because you don't really want to do much monitor repair in the field, you simply want to have a spare if you have one and swap it. After the monitor's been sitting for a while, the picture tube mysteriously recovers some of its charge. This is really important. Just because you've discharged it once and removed the second anode, don't go sticking your tongue in that hole down there. that thing can recover some of its charge. And in fact, let's take a look and let's see if we can see it. I'm going to try discharging it again. Let's see if we can see another little spark.
There you go.
Okay, and definitely, all right? Now, even if you get a shock, even if you get a shock from the second anode, the shock is not really very dangerous. It's DC, and direct current, it's just a static charge, just like when you rub your feet on the carpet. But the problem comes in that you jerk your hand back. The reflex action causes you to jerk your hand back and you lacerate your hand on the sharp metal chassis. Or you knock the neck board off. You elbow the big drunk guy that's looking over your shoulder and he pounds you to a pulp or something like that. I mean, I've even gotten shocked off the thing when it's been plugged in because I didn't realize it was plugged in, and I go to grab the thing. Gosh! So, you know, it's not something that'll kill you. You just have to... be kind of careful when you go to reconnect it that you redischarge it. So you redischarge it like that, and then using the grounded screwdriver, get both of those little fingers in there. Now it's kind of hard for me to juggle the camera and this at the same time, but basically what you do is this. Holding it like this, you put in one side like this, and then use the grounded screwdriver put in one side, use the grounded screwdriver to shove the other side in there. When you get it in there, look at it carefully. You know, tug on it, make sure that it's in there. Some people pull the wire like this and pull it tight. Don't be afraid to tug on this thing. If it comes off in your hand, it wasn't in there properly. You know, you should be able to tug on that and have it stay in there, and then it's okay. Okay, so that's really important. Yeah, Jeff?
I noticed that one had like a little washer on there.
Yeah, some of them do, and this is kind of a pain in the butt. Some of these second anodes, here's the two little fingers, and they've got a washer like this with a slot in it, like this. And I assume that washer is to keep the fingers together and to keep it solid and to make good contact. It makes it really difficult to get that thing in there. Some people pull the washer off and throw it away. I can't say that there's anything wrong with that. I don't, but it sometimes makes it kind of a pain in the butt. Okay. But this is all there is to a monitor. What we've just gone over is the entire monitor. There's really nothing else in a monitor. I mean, that's really all there is to it.